Hey guys. Alright, so everybody, listen up. We've got a speaker today. So you guys all know that Robin works in a startup for Alzheimer's, right? He's talked to you about that?
Yeah.
This is one of the founders of the company that Robin works with. Jason works with Alzeca, and he's going to talk to you a lot about his path and how he's gotten where he is. So I'll let you take it away.
All right, cool. Hi, everyone. Hello. So I understand you all are building cool stuff this summer. Can you all just go around and quickly tell me what you work on? Or what did you want to build this summer? Your name?
I wanted to build an RC tank controlled by a BSE controller.
Cool.
I'm working on my robotic arm. And
Very cool. I like that stuff.
Home security system that also comes with a temperature sensor.
Neat.
I'm building an RGB LED light display.
You're going to use it for your room?
I'm doing the same thing as Renan, being controlled by a PSE controller, super robot.
Why PS2? Why not like Xbox?
The Xbox is better.
Oh.
The Xbox is better.
All right. How about you?
And a solar power speaker system, and it can also charge for.
How do you solar power, huh?
I'm reprogramming the camera to take time-lapse photos.
To like monitor plant growth, weather, anything, or what?
Something like that.
Cool. How about you?
I'm doing a voice control robot.
Really?
Yeah.
What do you use for the voice control module?
Easy VR recognition module. It's a shield.
Okay, Arduino. And last but not least.
Oh,
Oh, I'm sorry.
Oh, I'm doing a wind turbine. They can
Wind
power
turbine.
LEDs.
I'm making an electromagnetic floater. Like, that's magnetic objects floating in midair.
Oh, like those globes and stuff.
Yeah.
Cool. That's neat feedback control. Cool. All right. Well, I'm not an engineer. We get that out of the way. I'm a biologist, but we do use engineering in what I do. And so I thought, so I'm an assistant professor at University of Houston. So you might wonder, how in the world to get there? Who wants to be a professor and why? When would we apply engineering to a job? And so how do we bring that in? So I'm going to tell you my career path in terms of how did I even decide I wanted to go to university? How did I end up there? And the same thing I might pose to you. You might be thinking, you're here because you're curious about how to make cool stuff, right? But you might think, well, what am I going to do in the future? And so I thought I might just spend a couple minutes talk about that. And as I'm going through, this is one of these things where you can ask me questions. I know you could just sit there and and if I'm boring, say, be nice. But I'll try to keep this kind of interesting. Oh, and could we kill the lights? Or where are they? Oh, here. I don't want to put you to sleep. But just so you can see. So I'm a scientist, right? Not an engineer. So I do a little bit different. And I always look for these little memes on the internet, what do people think you do? And it's kind of weird because when I was a graduate student, I would tell people, oh, I work in neuroscience. Like, oh, you must be like a genius and stuff. I'm like, no, I'm just a guy. And so being a scientist or an engineer is a lot of fun. It's a lot. You can do incredible things with it. You can change the world if you come up with a really cool idea. We hope to do that in the field of Alzheimer's, which I'll tell you about. But essentially, everybody has a different opinion. But a lot of it turns out to be hard work, understanding, knowing the nitty-gritty details when you do whatever you're working on. Knowing your stuff, being a good craftsman is a really important part of being a good scientist or good engineer. Now, how did I get into doing biology research, leading to what I do now? Well, when I was a kid, I was actually interested, and I'm still really interested in lots of stuff. So I was really interested to hear somebody's building a robot arm. I had interest in delta arms. This is sketchy. Simple drawing robot. It's a delta robot. I'm interested in microprocessors. So I do this stuff in my spare time. So I like it, and I can relate to what all you all are doing, especially Arduino stuff. It's a lot of fun. You get a big bang for your buck with this. But I was also kind of a nerd as a kid. I liked Doctor Who and all the sci-fi TV shows. And you know, so that stuff sort of, I would watch these shows and get ideas about things I wanted to do. And I started to get this idea I wanted to do things like combining some engineering. So we have tissue engineering up on the right here. This is artificial skin that's used in patients. I thought that's really kind of interesting. But when I got into biology, that was not very well developed. And so I looked at it and said, I like that idea, but I'll put it aside for a few years. But one of the things I was, and I was also interested in botany, plants. So I grow carnivorous plants as a hobby. So I do lots of kind of nerdy, weird things, but I have a lot of fun at it. But one of the things I was always interested in, and has always captured my imagination, is the brain. Artificial intelligence, understanding how this 3-pound gray matter in all of us, how does that work? How can we think? It's the most complicated machine in the universe. And trying to solve that is no easy task. It's the hardest task there is. But it always presents something that's interesting and challenging whenever I work on this. Now I should tell you that my interest in being creative and discovering things this is kind of in our family. I just thought this was historically interesting. On the left here, we have the Mercury space capsule. So you might remember that's one of the first manned capsules in the United States program, way back in the 60s. And my granddad, shown on the right here, is sort of a little below the signature of Neil Armstrong. We have this weird-looking thing. This is actually the heat shield that my granddad designed. That was a modified version of it. Was put on the Mercury space capsule for re-entry. So I guess I got my love of invention and discovering new things from him. Now, so I had all these interests in high school. And when I went to college, right, so I'd studied these and done some stuff. When I went to college, though, this is Wake Forest where I went, I was presented with this choice. You know, what to do. And this is a hard thing. So some of you may be like, yeah, I'm going to be an engineer. And others of you may be like, yeah, I really like this, but I don't know if this is what I want to do. And what I'll tell you is to really be successful, you have to do what you like. You should never let somebody just dictate to you. You should be a doctor, engineer, or something else. You have to feel it and like it. And originally, I had thought, I want to go be a biologist. So I took some intro courses. I was like, these are terrible. Terrible. I don't like them at all. They're boring. Oh my gosh, that's hideous. So I said, after the first semester, I think I got a D in the Intro to Biology course. So even if you get a bad grade in one course, you can still go on to become something you may not originally liked. But I said, I'm done with biology. But I really like reading and writing, so I'll be an English major. And I did that for a couple of years. Then I said, yeah, I like this, but there are no jobs out there. I want something where maybe I can make a living. And I really still like biology. So I decided, as part of my career path, I'd go, and I had almost finished my degree in English, but I decided I'd go back and I'd get a degree in biology. So I actually have 2 degrees, one in English and one in biology. So I combined those as I've gone through. And once I was finishing up my undergraduate at Wake Forest, I decided that I wanted to go get a PhD, doctorate degree. Some of you may decide to do that if you really like school. I went up to Chicago and got my PhD in developmental neuroscience. So that's looking at how the brain develops. Okay, so, and what I was really interested in was looking at a human aspect. Because I like the idea that I can make something or discover something that's going to help people. That's the big motivator for me. So I did a lot of research for about 4 years on fetal alcohol syndrome, which is if a woman's pregnant, she drinks, then it can cause birth defects in the brain. So the idea was to figure out how can we treat that. And that was a very interesting project. And I was really interested in the brain and stuff, and I love doing that. But eventually I got to the end of that and said, well, this is kind of interesting, but I don't feel really passionate about it. You spent all this time on it and said, it's kind of interesting. Around that time, this was about 2000, so a little while ago, but I was getting ready to finish up my PhD. Those are about 4 years, advanced degrees. And So I said, well, what else can I do? And I had a friend who went to Florida. He went to the Mayo Clinic, which is up on the top here, so the building. Mayo Clinic is really well known. It's a very famous medical research institute. And one of the areas they're known for is Alzheimer's research. And Alzheimer's, how many of you have heard of Alzheimer's? So all of you, I'm impressed, okay. That's good. So what's Alzheimer's disease? Anyone?
You forget stuff.
Exactly. That's the biggest thing, right? Everybody knows you forget stuff. And that's essentially the forgetting disease. I'll talk a little bit more in detail in a few minutes about that, but essentially that's what I studied for a number of years. I'm going to show you one of the early successes I've had. It was really exciting. It was my first project. And eventually, just to tie that up, basically I came to University of Houston. So I've worked on Alzheimer's from 2000 onwards. Okay. So what is Alzheimer's disease? Well, briefly, it's that forgetting disease. It was discovered it was reported first in 1904, so we've known about it over 100 years by this guy, Dr. Alois Alzheimer's. He was in Germany, and he wrote about this lady on the right. Sorry, these are kind of hard to see. Her name was Auguste, and when she was about 65, she started to show these really bad memory losses. Not just like forgetting your keys, but you could tell her something, and then a minute later, she'd completely forget.
And that's the same question. Yeah.
Huh?
And we'll ask the same question?
Yeah, she would ask the same question. So so you might have had some personal experience with somebody like this, or maybe a grandparent. Unfortunately, more than pretty much all of you will run into somebody with Alzheimer's disease as you get older. And one of the reasons I went into Alzheimer's disease is that 2 of my grandparents developed their Alzheimer's disease-like symptoms when they got older. So when I was finishing up my PhD, I thought, this is terrible. And that really compelled me to go start looking at this disease and trying to find a cure for it. Who's affected by it? This is just to give you an idea of context and why did we start a company? Why did we found a company? But basically, there are millions and millions of people who are affected by this disease. To give you an idea, by the time you're about 80 years old, you have 1 in 2 chance of getting Alzheimer's disease. So it affects a huge number of people. By 2050, it's going to be about 14 to 15 million people in our country. So it's an enormous problem, and there's no treatment for it currently. Now this part, I can talk a lot about it, but I thought I'd show you a short clip, just so you can have an idea of what a patient with early Alzheimer's looks like. The sound might be a little bit faint. Oops, sorry. Here. Let's try that again.
Some of the questions that are asked today may be tough for members, and the reason that we ask questions that are tough is we want to strengthen memory. We want to find out where any memory thinking problems might be. And if the questions were all very easy, you would be able to answer them a little
So that gives you an idea. You tell somebody something and they immediately forget it. And this is a big problem. And this is the first part of Alzheimer's. That's a mild patient. By the time they have severe disease, they can't take care of themselves, they can't interact with anybody, they require full-time care. It's a big burden on both the parents and family members who all have to take care of, say, a grandparent who has this disease. And so, what causes this? What do we see? This is all leading up to what the product that we're developing is. But basically in Alzheimer's disease, if you look over here, see, this is a cartoon of a normal brain. And here's a brain that's been affected by Alzheimer's disease. Same age. So these might be both 80-year-olds, but you can see, if you overlay them, how much more shrunken the Alzheimer's disease brain is. So the way to think about this is essentially Alzheimer's disease is this massive, massive destruction of brain tissue. That's what goes on. And what causes that, we don't really know. We think that there are these substances. This is a microscope slide of these substances. They're called plaques. And so plaques accumulate in the brains of patients, and somehow they drive the destruction of brain tissue. So a lot of people have been developing or targeting those plaques as a way of treating the disease or diagnosing it. And billions of dollars have been spent on this. Okay? Most of them medications. So we see in the last few years about $160 billion just in the US has been spent on it. It's a big market. There's lots of things. There's a lot of opportunity to make cool discoveries and help a lot of people if you can find something. And that's kind of what drives me. I look at this, I've had experience with it and said, how can we make this better? Right? So I've had this big interest in history in developing, or I've tried to at least, in developing medications for this disease and also diagnostics. So the first part are medications. I don't know how many of you are familiar with the journal Nature, but that's one of the top science journals. And my very first project, when I got out of graduate school, was I came to Mayo Clinic, and the very first paper that we had appeared on the cover of Nature. This is where they described the structure of DNA. Crick and Watson in the 50s, and lots of discoveries. But I was here, so I felt very lucky. I was in the right place at the right time. And sometimes making discoveries, whether you're in science or engineering, is being with the right group of people, right? So that stuff you can't really prepare for. You just discover that. So basically, we found this medication. I found it actually at the bench. I was working, and I found this cool thing and said, oh, and I won't go into bore you with all the details of all the biochemistry because it's a bit complicated. But basically, it's a drug that was called fluorazine. And so I found it at the bench, and then we patented it and licensed it. And this company called Myriad Pharmaceuticals, they're up here. They're in the news every once in a while for gene patents and stuff. But basically, they bought the license to this. And it was pretty cool. I would send these articles to my parents. Oh, look, there's this one in Business Week. It's on CNN. They were following these trials. All these people are getting these drugs. And it's getting really exciting. So about 2001 is when it first got licensed. And then in 2004, we start to see these initial results. And we got like these cool results. So this is, these are the three groups. You can't see that. University of California, San Diego, Mayo Clinic, where I was at. And then Myriad had this partnership. And when they treated people for like 2 years, and they look at their mental state, they talk to them, just like that thing you saw, that videotape, or that tape. Basically, people who got this drug, a percentage of them didn't decline. They were totally stable. And this is like questions that you could answer properly. Okay, so it's just they test them over time. And this is in contrast to these other people. They didn't get the drug, or they got a low dose of it, and they all declined. So people are going like, hey, this is really cool. Oh, this is the next big drug. And it was like featured in these journals like 2007 and all this cool stuff. So it's getting exciting. Now, I'm just watching it. I made that discovery, and then they licensed it, and the big drug companies do all these trials. That's how it works in science. Also, if you're an engineer or something similar, you might come up with this cool idea and refine it, but then it might be licensed to somebody else like Johnson & Johnson, and they would refine it and do additional tests on it. So you might be involved at the first part, middle part, or the end part, depending upon what your engineering expertise is. Did you have a question?
Yeah.
Yeah, sure.
Do you get paid?
Do you get paid? That's a great question. Sort of. So the way these things work, like if you're a biologist, right? You're an engineer. So engineers might make cool stents or something to put hearts or pacemakers or something. The way it works if you're at a university is you make these discoveries and you get a patent. And the patent is owned actually by the university, and they give you a percentage of whatever they get. So the way companies work is that if your invention is successful, your drug is successful, they'll get royalties, they'll get payments. But if it doesn't work, you probably don't get anything. I got $1,000 from the total 8 years of trials. So not much, but it was very exciting. It was like a lottery, right? Can't win if you don't play. So this was kind of cool. And basically it was 7 years, almost 6,000 people. They tested this discovery, this drug in lots of hospitals, and they spent about $100 billion. You know, so I remember, I think it was in 2008, and I had started you can't see this, but this is July 1st, 2008. So it was 1 month after I started at University of Houston. I thought, well, maybe I could give up my day job if this drug was successful. Well, it was not to be. So it actually did not improve when they looked at 6,000. It worked in a small percentage of patients, but when they looked at everybody struck by this disease, it did not work. So that's disappointing, but that's life. It's part of being a scientist or an engineer is that you can be real creative and make all sorts of cool discoveries, but sometimes they just don't work in patients. But that's okay. But it got me interested in thinking, well, why did this fail? Right? And one reason we think it failed is that diagnosing Alzheimer's disease and looking at how the disease progresses and whether the drug works or not is a really tough thing. In fact, the only way that we can diagnose Alzheimer's disease right now is exactly what you saw in that videotape. It's, you know, if you think maybe grandma has Alzheimer's disease, she's very forgetful, there's no blood test, there's nothing right now that we can use to tell that. The only way you can do it, you can go to like a nice guy or nice gal, a neurologist, and what they do is they ask questions just like what you saw. And that is the way we diagnose probable Alzheimer's disease today. That's kind of like heart disease, right? Somebody has heart disease, they go in and say, oh, my chest really hurts when I exercise. Oh, you must have heart disease. Not great, right? So it would be kind of cool if we could get something where we could get a non-invasive test to say you have Alzheimer's disease or you have probable Alzheimer's disease or not. And, you know, so right now that's what we're stuck with. But people are really, including us, are really active in developing these new kinds of tests. So there's one where you can take blood, where you can take what's called cerebral spinal fluid. It's fluid inside your spinal canal. Not very pleasant. They have to use needles to get it out. But they test this. They use what's called a biochemical assay. They look at the amounts of proteins. Or there's this drug called, it's a radioactive drug. You inject it, and it goes into the brain. And patients who have a lot of that amyloid protein that forms those plaques that I mentioned earlier, that lights up. And so you can say, well, here's a normal person. Here's somebody who might have Alzheimer's disease. So those are sort of what people have been doing. We've been developing something that we think is a lot better. I want to show you that. Well, so this kind of leads from the last one. So my thought when we had these failures is we need to develop better tools, right? And hopefully something that people could use. So the reasons to do this are we get better medical care. You can diagnose people. Your grandma or granddad walks in. They could get a simple test. We could say, oh yeah, they have that, and then the family could help with this disease, you know, so people know what's going on rather than being scared. Knowledge. We try different things, or we want to see what affects disease, maybe diet and exercise, for instance. You could use something to monitor this. And last but not least, things to speed up trials. ways to evaluate disease. So those are the things, the reasons that I wanted to develop something better than just interviewing patients. So what do we do? So this leads into what we're doing and the basis for the company. The company's called Alzeca. But we're developing better diagnostics and therapeutics. Okay, these are next generation, sort of advanced technology. And so it's a little hard to see, but this is my collaborator, Anthony Pagata. He's at Texas Children's / Baylor, so that big hospital downtown. And these are some of the people on my team who've helped to create this platform technology. All right. And so essentially what we're doing is we're doing something called nanoparticle-based imaging technology. And this uses advanced engineering. So it's like sort of chemistry, engineering, to make what are called nanoparticles. Now, how many of you have heard of nanoparticles? Anyone? Sort of? So what are okay, so I'll tell you what nanoparticles are. They're very, very small. In the nanometer range, that's billionths of a meter. Really small particles. So this is a blown up cartoon. Okay? And so what you see is this is like a fatty droplet. It's made of fat, essentially, that's been engineered to contain a cargo of some sort. Okay? And on the exterior, it looks sort of fuzzy. If you were to look at it under a very high-powered microscope, it would actually look sort of fuzzy. We have a surface chemistry on there that we can make this into essentially a smart particle. It can go and bind to anything that we want, which is kind of cool. You think, oh, you could use it to bind cancer cells. You find something expressed on the surface of a cancer cell, for instance. You could make this, you inject it, and it sticks. It's like a dye sticking to cotton, and you could think of it that way. Similarly, we make this bind to amyloid plaques. So we modified the surface of these particles so that it can stick to plaques. And to give you an idea how small these are, this is a red blood cell. Super small, I can't see them in microscopes. And that's roughly the size of our nanoparticles. We can make a few 100,000 of those fit inside a blood cell. So they're really tiny, but they can carry all sorts of cargo. So they're a smart particle. The cool bit is we can do all sorts of cool stuff like this. This is a living mouse where we've loaded with an imaging agent. So this means it's something we can see on X-ray. This resolution is, you can see all these things are blood vessels inside the skull of the mouse. To give you an idea of how big that brain is, if you look at a dime, it's smaller than a dime. So we're seeing this in a living mouse, 3D, real time. Oh, this has been post-processed, but it's really pretty cool. It's amazingly high resolution stuff. And we're using these nanoparticles that have been modified to bind to amyloid plaques to look at patients' brains. That's what we hope to do. This nice 3D structure here. So what we do, well, it's hard to see, but we use a mouse model of Alzheimer's disease. And basically, these mice develop lots of plaques that we see here. This has been stained, so they're like blobs of protein inside these mouse brains. And when we inject you can't see this here either, but when we inject these nanoparticles into the bloodstream, basically they bind this is supposed to show you from the front to the back of mouse's brain, but basically they bind to plaques all throughout the mouse's brain. So we have, that's one thing that we see. And the other thing that's pretty cool is that when we load these nanoparticles with stuff, we put cargo inside, so they're acting like a Trojan horse. You guys have heard of Trojan horses. That's where Greeks hid inside a horse and then came out. That's what, we also call these Trojan horses, right? You can hide something in there and you can get it to the brain. And so here's an example where we showed, we just put a red dye inside the nanoparticles. The outsides are kind of green. And so basically we can see that they all accumulated plaques. And this is just a particle we haven't loaded with anything. So it just serves as a control. But essentially it tells us that we can target all sorts of drugs into the brain, which is pretty cool. Now, where's this going? So I just wanted to give you a little overview. That's kind of a long introduction, but basically, when we got all that stuff working, it's pretty neat. And you can see how big the market is, right? So there's a clear need for something like this. And so we decided to form a company. We call it Alzeca. It stands for, well, the way we came up with this is my founder, Dr. Anna Pragada, said you should always have, the first part should have something to do with your, whatever you're targeting. So in this case, Alzheimer's. And then these are the initials of the founders. So Erickson, that's me, Cook, and Anna Pragada. And Steve Cook is not on here. But basically, this is Robin. Of course, he's the CEO of our company. It's me. This is Anna. And then this is Eric Tanifum, who's our chemist who helped to engineer all these particles. And so basically what we've done with this is we have been developing this technology, and we've had a lot of interest from different people. And I just wanted to show you one closing slide. We've met a lot of cool people. For instance, we got to go to the Googleplex and talk to people at Google about perhaps financing some of our stuff. And that's been really interesting. So I got to meet people like that, people from SpaceX, some of the people who funded SpaceX. You might have heard about that on the news, and a variety of other people. But it's been a really interesting time. And I think with that, I shouldn't ask too many questions, but if you have some, I just want to close. And thank you for your attention. Yeah.
Let's say I'm gonna have Alzheimer's by the time I'm 85. Can you like see if somebody my age now have symptoms? Like, can you?
No, that's a really good question. So the answer is not usually. So we don't know. So Alzheimer's takes years and years. It's like 20 years. You start getting sort of things that could cause the disease. It takes a really long time to develop it. Now there are some people that they're in their 20s, not teens I think, but in their early 20s, they actually get Alzheimer's disease. Those are known as early onset. They're really rare though, like maybe 0.5%.
Oh, can you prevent?
No, not currently. So that's like one of the things that people have like tried to develop something to treat it. So like we're trying to develop medications, right, that you could take to like stop it.
Yeah.
One of the things though that's sort of interesting is they think exercise is really good for you. We have, one of the things we do in the lab is we actually do exercise studies with mice. They run on treadmills, and it actually seems to make them better. Yeah. So that's been really interesting.
I heard that when like elders walk a lot or exercise, like they are less likely to have Alzheimer's.
Yeah, that's been in the news a lot. So exercise seems to be really helpful. So we always tell people that's one of the things that you should do if you think you might, if you're worried about getting it. Any other questions? No? Any questions about the company that I can answer? Or how you do that?
How do you guys get, how do you guys, find each other to set up?
No, that's a good question. So, so how do you start a company, right? You have a cool idea,
Yeah.
right? And so how did I do it? So when I was in graduate school at a web design company, I always love finance and have loved taking ideas come up with and turning them into something interesting. This one I didn't even think about forming a company. So what happened was that I went to I got invited, I was in Germany, okay? And I was giving a talk in Germany. And I flew back and I had a message on my telephone when I got back. And there was somebody from the Alzheimer's Association there in Houston, and they said, hey, would you want to come out and talk to the public, as part of just public advocacy and tell people what is Alzheimer's about? And very, very basic, a lot less technical than this. But I said, I flew 9 hours and it's tonight. Okay, all right, Richard, I'll come out. So I went out to this talk, and I'm sitting on this panel. There's a senator there, and there's some pretty well-known people. I'm just this little faculty guy, this little professor. And so I was answering questions. And then there was this guy in the back of the audience, and he kept asking me questions. And I was like, who is this person and why are they asking me all these questions? They were nice questions, but so I kept answering them. And at the end, I was walking out and he came up to me and said, oh, Dr. Erickson, nice to meet you. And I said, well, thank you for asking me all those questions. It was nice to talk to you. He said, oh, my name is Steve Cook. And so is there anything that you have that I can fund? Can I give you money for something? And I said, I don't know. I don't think that way. I just like asking interesting questions. Well, the short version of it was we just talked for a while, and I said, well, there is this one thing that I have this friend at. He was at Texas Children's, but Dr. Anna forgot. I said, I have this friend, and we're working on this cool imaging technology to look at Alzheimer's disease. Oh, that sounds interesting. And so we did a lot of work, and then he was actually, Mr. Cook was actually very helpful in helping to get a car company started. So we got to the right point at the right time, and he helped us put everything together. And that's actually the way, if you have a cool idea, the way to start a company is talk to people. Because very few people are successful by themselves. That solo inventor who doesn't talk to anybody is somebody who will not be a successful inventor. You really have to get out there and you talk to people. And that's how it works in this kind of thing. It's all good relationships. And so yeah, and it's been a lot of fun. You meet all sorts of really interesting, people from all walks of life when you do this stuff. So it's neat because it's a good distraction from my regular job at the university. I meet a lot of different people that I would not meet at UH. So any other questions? Not really. Mary?
How'd you meet Robin?
Oh, how did I meet Robin? So I didn't actually know. So Anna Bragada, my collaborator, actually he knew Robin for many years. They had done, I think, 2 or 3 startups together. So Aneth he has a medical imaging company, he has a diabetes company, and I just met Aneth by talking to him, and so we kind of got this collaboration. And then he said, well, I have this idea for a good CEO. There's a good CEO I know. His name's Robin. And so Robin interviewed, and I liked him. Aneth, of course, knew him. And so I just got to know him through that route. But again, talking. So that's the best way. All right.
What was the hardest part about getting this off the ground?
Hardest part about getting Alzeca off the ground is money. I'm sure y'all are familiar with that, getting more cash to do stuff. And you have to have cash to do things. So fundraising for something like this is really tricky. You have to find somebody who's a real believer in what you do. Doing something like this is complicated not only from engineering standpoint, like making good or making the thing we're looking at, but also finding somebody who wants to finance that is a tricky business. It takes about 8 to 10 years for most drugs. So the thing I discovered in the lab, for instance, that Florazin, it took 8 years and $100 million. Yeah. So you have to find somebody who has deep pockets and is willing to wait a long time. This is something very different from, say, if you're an engineer, right?
Yeah.
You either make it, you make software, right? Software, you make it either works or it doesn't, and you're done with it. Biology stuff, you have to make it, show it works like in a test tube, and then you have to try it in small collection of patients. Is it safe? So do they die? And you hope that doesn't happen, because if it does, you're done. But so you have to try it in that, and then you have to trust a larger number of people, and you have to find people each step of the way willing to give you more and more money. And most people don't have $100 million laying around in their sock drawer. So you have to go out, and Robin, for instance, is very good at that. He goes and he talks to, they call them angel investors. They're people who have made money in other things, real estate, oil, or biology, biotechnology or something. And they say, yeah, that's a great idea. And they start giving money. And then if you're successful, it kind of grows. They'll put more money in, and
Will you have to pay them back eventually?
oh yes.
Like,
So
the
oh
money
yeah.
that they gave you, you have to give them back, or?
Oh yeah.
Or
Well,
that's
they're
the
not
difference?
silly, right? So
So what about if you're not successful? How can you pay them back?
you can't. This is the risk, right? So it's all business is kind of a risk. It's one of the things that what investors want. So venture capitalists. So Google Ventures, this is an example of VC group that I showed up there, right? They want 30x return, 10 to 30x. So that means that if they give you $1 million, they want about $30 million back. Why? Well, because they could put it in something else, right? You could put it in the bank, and you get some money back, right? It would be very safe. The true thing is that a good investor will invest in many companies, and only some of them will produce. You know, and everybody thinks their idea is going to succeed. Otherwise, why do it? We think ours is going to work. And so we have some investors that are early stage that they hope to get a very nice, if you get in early, that ground floor, you hope to get more money back. And so, but that's the thing, right? You have to find somebody who
So
really,
there are risks too, right?
very much so, right? Because there's a chance it won't work. The other thing is, so if you're an engineer, right, you have a cool idea, better mousetrap, to use an overused example, right? This is the most awesome mousetrap ever. And then you go and find some people to invest in it. What happens if nobody buys it?
They lose money and you.
Yeah, because you probably don't actually, because you're the one who has a cool idea, and they know the risks. That's just too bad. But they will often take your invention and they'll go market it.
Yeah.
They'll take control of it, so you own a percentage of it, not the whole thing. That's typically how it works. Because if you had a lot of money and you gave it to somebody, you wouldn't want to just let them do whatever with it, right? You'd want some give and take. And so that's how it works with us too. There's always give and take, and try to do what's best for the company and how you can make it grow.
Is there a limit to how many angel investors that you can get?
Yes. So for most startup companies, like we're what's called an A round biotechnology company, there are a lot of people like us that do different things. You don't want to have hundreds of people. What you want is you want to get a few people who have deep pockets. And what they can do is they'll give you a little bit of money at the beginning, and if you do good stuff with it, they'll give you a lot more. And then they own a greater percentage of the company, and they can kind of call the shots and help you out. So the answer is that some companies can have hundreds of investors, but most don't. They might have 10 to 30 max. Too many people, it's like too many cooks spoil the broth. Everybody's saying you should people say go this way or go this way. Really, you want a few people who have a good understanding of the environment. Like say you're doing aerospace, right? You'd want somebody who's an investor who knows aerospace, and they'll want to give you money to say that's a great opportunity. That's the same thing you want with, if you get people in a company, you want them to know, that's a great opportunity. I'm going to give you a lot more money. The worst thing in the world to get is what you call it's called big dumb money. It's you get somebody who gives you money, but they have no idea of the opportunities or risks, and they're just like, oh yeah, here's some money, and then they're mad when you don't make your first success because of some technical. So the idea is to find smart investors who have a lot of money, and that's hard to do. So yeah. All right.
Well, there's nothing else you guys want to ask. Well, yeah, say thanks.
All right.